Okay, great. Third group.
Okay, so good afternoon, everybody. So what our group has discussed and is proposing to you this afternoon is a blueprint for a research goal that we find exciting, which is developing material systems that can adapt and evolve to optimize specific performance. One possible example is a library of peptides that can adapt in response to external energy sources in the presence of different environmental cues. Or another example.
I can give another example. We are thinking to build a synthetic system that can pass the Turing test. For example, we can build a protocell and let it communicate and interact with, for example, a bacteria. And it is able to secrete chemicals that triggers the bacteria to respond. But the bacteria won't be able to tell. Like it would respond as if our protocell was another living material. So that's our test method. And all of our systems will be non-equilibrium systems. It will be powered by output energy, like light, electricity, or magnetic field.
And so essentially, as of today, this is a domain that is governed by essentially synthetic biology, or there are some in silico systems. So essentially, this was never done from scratch, essentially.
So what is new in our approach? We discussed about it since we are targeting something that is brandly new. So we assume as long as we find some ideas to approach this question, it's considered as a new approach. And so specifically, we will focus on controlling what Lee called constraints here. So like kinetics, time scales, length scales, basically a set of boundary conditions that you can impose into your system. And we will consider these different sets of constraints as our memories, either it's short-term memory or long-term memory, whether it's volatile or it's permanent or how transient it is, depending on different process kinetics. Because all these memory capabilities, it determines our adaptation and evolution behavior. So that's our perspective in approaching this. Yeah, and if success, okay, I think that's this. Yeah, do you want to comment on the...
Yeah, so one particular aspect on which we will focus is the flow of information and energy in our system, which we find central to the operation of our systems. And for example, like in biology, we have ratchet systems that govern the absorption of energy and its exploitation. And these are Brownian ratchet systems. We have seen some of these even these days. And we think that that's key to the functioning of these materials.
So next, who cares? We hope that everyone in the functional materials field will be interested in this, and what difference will it make? So if really we can build an intelligent system, we hope to unlock systems that can optimize themselves and they can work collectively to produce the optimal performance. So specifically, what that means is, for our system, we want it to be adaptive and intelligent. For example, if we are targeting at 4 tasks, so with a self-adaptive system, it is always able to reconfigure itself. And when dealing with different tasks, it always keeps itself at the optimal performance. So instead, if it's a passive system, you can, of course, build in 4 tasks into your system, but it won't be that a single system is optimal for all 4 of them at the same time. So that's our vision here. Yeah.
And we see 2 risks out of actually many. So one is matching the constraints, essentially, so the kinetics of the systems. And then we also see the problem of the systems evolving and being trapped in kinetic traps. So not being able to reach the optimal state, but being trapped along the way. And we also consider the cost, essentially. And we think that this is a topic that could be approached by a multidisciplinary team composed by synthetic chemists, physical chemists, modelers, material scientists, and also biologists, for a total of 16-year person, essentially.
So for Yeah, for how long it will take, we expect it to be 4 to 5 years, but it really depends. Actually, it's also one risk, one challenge we see here, because as we are building in more and more complexity into our system, as we start to have more like memory, more decision-making process, the computing power for our intelligent system, the requirement will scale exponentially. So how long it will take, it also depends on the development of the software and the computational model, things like that. Regarding our midterm and final exams to check for completeness, so our midterm goal is to build a out of equilibrium system. As I said, it can always optimize itself to give you the best performance. That's what we call adaptation. And our final goal, as an intelligent system, we hope it can, this is actually inspired by the molecular printer from yesterday's talk. So we hope to build a first generation materials. We set everything in and we keep the energy on, we leave it alone. But then everything starts to run autonomously. Our first generation material will be able to adapt, to evolve through this adaptation process and remodel itself. Then it is able to produce a second generation of materials, which gives you better performance. And throughout this evolution cycles, these better or fitter ones will survive, and those less capable ones will be killed. So this is our picture here.
Wonderful. Thanks, guys. Questions, comments? Anna, you start.
Sorry, it's a wonderful idea. I might have missed this, but do you have an example of a system that you would start to work on?
Do you want to comment on the Protel cell?
Yeah, I mean, so I don't want to refer to work that's been done in the past, but there are examples where people have done a hybrid materials generation system in a robot that produces the materials, then puts them through a kind of a maze, if you like, where they get killed at the end if they don't survive it. If they get to the end of the maze, they are selected. If they die en route, then they are taken out of the game. So there, you can use that for inspiration to build a hybrid robotic chemical system that would have some kind of autonomy. But that's just one example. I think these guys, we envisage something a little bit more fundamental, looking at the constraints at the beginning, if you want to make any comment there, but there are existing examples.
I wanted to just give you another example, since Turing test was mentioned here, and that is that you can have protocells or synthetic cells that can act as translators between two completely different species of bacteria or life forms. And this would lead to making assemblies, morphogenesis, if you want to call it, that is different from what you see with pure life forms. And that itself would be a step forward where you have different functionalities built in by using different life forms and synthetic cells.
Really interesting idea on the characterization side. How do you plan to characterize this material and at which time point? Because you mentioned you construct the first generation material, you leave it be. So, like, well, what's your plan there?
So I can say some quickly.
Sure.
Sorry. Do you want to say? I was going to say that the characterization is does it live through the assay or die, right? So I think you have to set up the environmental fitness function. So such that let's say you want to make a better conducting protein. Okay? So you have a bunch of proteins falling down a track, and at the end you measure the conductivity, and if there's no conductivity, you don't open the door, and then you just flush them away, and if there is conductivity, you open the door. I just made that up just now, but you can imagine something like that, right?
Okay.
I mean, but you have a fitness function there. So I think really the important thing is it allowed to persist? And then those constraints that gave that persistence then used again. So I think this is something they pushed on very hard when I was being a naysayer during the entire time. So these guys have done a brilliant job actually of kind of battling past that. So the thing that is very important is that they kind of come to the conclusion it has to persist, has to survive, has to overcome the thing you want it to resist against. So maybe you can have a very material that normally hydrolyzes at low pH. So what you do is you just have a low pH medium, hydrolyze everything, and the stuff that gets through, you say, well done, I'm going to remember the constraints because you've been tagged, and do that again. I don't want to add anything.
Yeah, I can add a bit on how we plan to test our system. I think for testing, we need to sort out a criteria or a list of qualities it has to meet to be considered as an intelligent system. For example, the sensing perception, that's the basic thing. And when you can sense something, you should be able to respond. Then you can, whether that can be remembered as a memory, whether you can learn, and that learning capability can help you to evolve, to respond differently, more intelligently in a second test. So this, but this is just a part of this list. I believe there's a whole list of things you can define your system as intelligent.
Well, maybe I can jump in with a comment stimulated by your question. That is that actually our approaches, our backgrounds, our areas are a little bit different, so maybe that's also why we didn't go too deeply into a specific system. But I would say that two things that have emerged, or we can say, one is that measuring changes in concentration, as was said today, is something that can be challenging, so maybe that's an open challenge for, let's say, the area. And also I would say that chemists are quite good in measuring concentrations, but we are not so good in measuring fluxes. So we can know how many people are on the two sides of the bridge, but we don't know how many are crossing the bridge. And in many cases, many, especially theoretical theories, they are based on stationary states considerations. And so maybe from a technical point of view, being able to measure rates rather than concentration might advance this area and also others, but that's more a comment stimulated by the question.
Thank you so much.
Welcome.